Listen closely to that high-pitched whistle and flutter at the end of the rev. That's the sound of an engine doing something entirely unnatural. A standard, naturally aspirated engine is limited by atmospheric pressure. It pulls in air on its own to mix with fuel and create combustion, breathing much like a human runner out for a jog. For decades, making a car go faster meant creating a bigger explosion in the cylinders, and the only reliable way to get a bigger explosion was to build a physically larger, heavier engine block to hold more air and fuel. But adding weight to a car makes it harder to accelerate. Engineers eventually hit a wall of diminishing returns, needing a method to make a compact, lightweight engine breathe like a massive V8. The solution to that weight problem is the turbocharger. It's a relatively compact metal housing that attaches directly to the engine's exhaust system. This hardware forces air into the cylinders at extreme pressures. It alters the thermodynamic cycle of the vehicle, and in the process, generates that signature, high-pitched acoustic profile. By cramming more oxygen into the exact same physical space, it acts as a mechanical cheat code. You multiply the horsepower output without adding the heavy iron of a larger engine block. We can actually hear this physics problem being solved in real time. The first acoustic phase is the deep rumble of standard combustion. Normally, an engine wastes a massive amount of its kinetic energy and heat by blowing all that expanding exhaust gas straight out the tailpipe. A turbo routes escaping exhaust gas through a spiral housing to violently spin a turbine. As it spins, generating a high-pitched whine, a metal shaft turns a connected compressor wheel. This wheel sucks in outside air, forcing a dense, oxygen-rich charge into the engine's intake. That escalating whistle you hear from the driver's seat is the sound of a machine intercepting its own waste, recycling it, and using it to power a closed loop of highly pressurized energy. But before the power hits, there is a third acoustic phase, a brief moment of mechanical silence. Car enthusiasts know this dead zone as turbo lag. This chart mapping pedal pressed against power delivery illustrates the problem clearly. You can see a visual gap here on the timeline. When the driver floors the gas, the engine needs a fraction of a second to burn enough extra fuel and build up enough hot exhaust gas to spin the turbine up to speed. That mandatory delay is the lag. Then comes the final phase, the boom. The pressure threshold is met, the compressor suddenly pushes against air directly into the cylinders, and the vehicle delivers massive, explosive acceleration. A four-cylinder engine with forced induction suddenly generates the torque and speed of a heavy V8, while remaining lighter and burning less fuel during normal city driving. Despite that momentary delay in throttle response, the turbo severs the traditional link between a vehicle's physical footprint and its maximum power output. If forced induction generates extra power and maintains a lower weight, it raises a clear engineering paradox. Why do manufacturers still build cars without them? To safely force highly compressed air into an engine, you have to support it structurally. You need extra oil lines to lubricate the spinning turbine, complex plumbing to route the air, and large intercoolers, essentially radiators, to cool down the air charge before it detonates. Cramming all of these components into an engine bay means manufacturing costs jump. Furthermore, you have delicate moving parts spinning at over 100,000 revolutions per minute at extreme temperatures, increasing the likelihood of mechanical failure. Automotive engineering requires constant compromise. You cannot achieve maximum horsepower without accepting higher financial costs, severe heat generation, and a stricter maintenance schedule. That high-maintenance reality sits in stark contrast to the vast majority of commuter cars on the road today. If a vehicle is designed strictly for driving from point A to point B, a traditional naturally aspirated engine is cheaper to build, requires fewer trips to the mechanic, and easily outlasts the life of the vehicle. Turbos are highly specialized tools. They are built for specific thrills and boundary-pushing efficiency, but they are absolutely a trade-off. It comes down to what you value most behind the wheel. Do you want the safe, predictable reliability of a standard engine? Or are you willing to deal with the mechanical complexity just to hear that turbine roar? Let me know what you'd choose in the comments.